title up here is Exponential Concentration in Quantum Kernels and Generative Modeling. I think we can all agree that that's quite a dry title. So when Marco sent me this message yesterday, I had an idea for an alternative title: Revisiting Barren Plateaus, a Ghost That Never Leaves, or maybe more accurately, Revisiting Exponential Concentration, a Ghost That Never Leaves, because actually what I'm going to talk about is symptomatic of a more general phenomena. And I warn you in advance that this is not a talk that I have done before, and it might be a talk I never do again, because I think it's a little bit of an experiment. Rather than sort of presenting the main results from a couple of papers, I am going to spend some time sort of wallowing in the weeds and presenting some subtleties we thought about in the run-up to the paper, some things that are hidden in appendices, and some things we've enjoyed thinking about during the response stage. Because I think these, I hope, can help you think about how to think about trainability in other areas. But with that in mind, if I've forgotten to define anything or assume too much, please interrupt with questions. Okay, so I am not going to bother to introduce variational quantum algorithms because I think I can assume that you're all quite familiar with variational quantum algorithms. I also imagine that most of you, unless you slept through Marco's talk, are pretty familiar with the problem of barren plateaus in variational quantum algorithms. Nonetheless, I will start with a very brief recap. So the barren plateau phenomena, as introduced by Jared McLean et al., is the observation that the variance in the partial derivative of the cost for a variational quantum algorithm, in many cases, in particular for deep circuits, scales exponentially with the number of qubits that your parameterized quantum circuit acts on. So if you combine this with Chebyshev's inequality, what you get is that the probability of observing non-negligible gradients vanishes exponentially with problem size. So for small-scale problems, you may have a reasonably textured landscape that you can train, but for large-scale problems, your landscape is going to become flatter and flatter. And because your cost is determined statistically, this means the number of shots required for training is going to grow exponentially with problem size. And I'm going to reiterate Marco's annoyance at how Jared McLean et al. Framed the original barren plateau problem in terms of gradients, because it just makes all your algebra a little bit messier and more annoying. You can, as Marco said, instead work entirely in terms of what is called exponential cost concentration. So that is, you can look at the variance of the cost, show that that vanishes exponentially, and as long as your cost is a quantum cost, with gradients computed by the parameterized quantum circuit, and it is bounded between sort of 0 and some finite number, then showing that this variance vanishes exponentially is equivalent to showing that the gradients vanish exponentially. And so combining this with Chebyshev, what you've now got is that the probability that the cost deviates from some fixed point vanishes exponentially with the problem size. And so the number of shots required for training grows exponentially, problem size. Or in the language of exponential concentration, what we say is that the cost landscape is exponentially concentrated towards some mu, so that is, with some exponentially high probability, the loss is equal to mu. Okay, and there are a number of different causes of exponential concentration, which you already know about, but I'm just going to recap quite quickly because I do have my own take on a few of them. So first and foremost, the choice in circuit, namely two deep circuits, as was shown by Jared McLean et al. We later showed that, sort of refined this result, saying that if your ansatz is too expressive, then you're going to have a barren plateau, but if your ansatz is less expressive, it can be either trainable or untrainable, depending on other factors. One of those other factors is how entangling your ansatz is. Another cause in barren plateaus, or exponential concentration, is your choice in target learning problem. And I'm going to spend a couple of seconds on this because this was something that Marco didn't mention, but is a pet interest of mine. So in this paper here, we showed that barren plateaus, well, you're unavoidably going to encounter a barren plateau, or equivalently exponential concentration, if you try and learn a typical random unitary, or equivalently a typical scrambling unitary. So mathematically, this is closely connected to expressiveness-induced barren plateaus. So the fundamental cause is sort of too much randomness, mathematically too much randomness. But conceptually, I think expressivity-induced barren plateaus and sort of randomness in your target problem-induced barren plateaus, because actually the result I'm talking about here is more general. So in this paper, we focus on learning random unitaries, but actually more generally, if there's too much randomness in your target problem, you're going to encounter exponential concentration in barren plateaus. I think these are conceptually different. So randomness, too much randomness from your ansatz versus too much randomness in your target problem. So that's why I've separated it out here. I also think it's worth making a comment on Ryan's presentation at this moment. There's something I was going to put my hand up and ask, but we're out of time. So I'm going to try and play the reasonable person who disagrees with the conclusions from your first part of the talk. So at the end of this paper, what we say is that, look, the fact that you're going to have bound plateaus when trying to learn a random unit tree doesn't doom variational quantum algorithms. It just says you need to pick your target problem carefully, and very random problems aren't good target problems for QML. I would make exactly the same point for your, I think they're really nice results, but I would say what they tell us is that we need to pick our target problem carefully, and actually there's not enough inductive bias or structure in those problems for learning random circuits. And actually another subtlety, so I feel like I'm just talking to Ryan now. I'm going to keep going with it. So our result on bound plateaus for crude learning scramblers. Bound plateaus and statistical query learning results, I think, are closely related. So there have been a couple of really nice papers recently doing something I had planned to do on my to-do list but hadn't got around to, showing that with statistical query learning you can't learn random unit trees. I suspect we could also show that it's basically barren plateaus that stop you learning your random circuits. Okay, that was a segue, the diversion. Next one, choice and cost function. So using cost functions that are global, you're going to end up with bound plateaus, but local ones, you can avoid it. In general terms, there were obviously a lot of subtleties that Marco was talking about. And finally, noise is another cause of bound plateaus. Okay, so Marco, in his last talk, just provided a nice unifying theory that links together these different causes of exponential concentration. Is that all there is to say? Are we finally done with bound plateaus? So I would say, sadly or happily not, depending on what your perspective is. First thing to point out is that the overwhelming majority of results on bound plateaus have been formulated, as Marco highlighted, for VQE style losses. So that is, you have some initial state, some parameterized quantum circuit, and then some measurement. And maybe you sum over a bunch of those terms. Often, implicitly also assume that you have to have at most a polynomial number of terms. But many losses of interest are not, or at least not obviously, of this form. So there's still work to be done trying to understand how bound plateaus materialize for other loss functions. By the way, I'm going to use loss and cost interchangeably. I can't help it. Secondly, the variance of the loss isn't the only thing that matters. So to illustrate this, let's consider the following super naive proposal. Could we solve bound plateaus just by rescaling the loss by an exponential factor? So the idea here, and excuse the terrible drawing, this was done on a plane. Take your loss, which has a variance that vanishes exponentially, just rescale it by an exponential factor, and then your variance is now going to be order 1, it's going to be bigger. Now, have we solved the bound plateau problem? Answer, no, because the effect of shot noise is also going to get rescaled by an exponential factor. So when you try and compute your estimate of the cost, there's also going to be more noise in it. And so you still won't be able to determine small changes in your gradient. So it's not only the variance in the loss that matters, also the interplay with shot noise is really important. And this is why I put my hand up to ask the question in Maria's talk. So I think in general, though I don't disagree with you, in general I think including shot noise is really important for benchmarking, because if you don't include shot noise, then you master the effect of exponential concentration. Because if you have the exact cost value, even if your costs are exponentially concentrated, you're still going to be able to determine very small changes in the cost, and so navigate. That said, I completely agree with what you did, is that it's only going to make it worse. So that's why I chucked in positive. So if you're trying to, and I'm probably preaching to the converted here, but when, I'm recorded, you do sometimes see papers where they do small-scale implementations without shot noise and then claim, boom, we avoid bound plateaus, or boom, this is going to be scalable. You cannot claim to avoid issues to do with bound plateaus and exponential concentration unless you're training with shot noise. So if you want to try and sell your paper, you've got to include shot noise. If you try to say that nothing works, then I agree that you don't need to include shot noise.
Sorry,
Cool.
I have a question
Yes.
about that. What about dilating the random variable data as well? Does it also affect the shot noise part?
What do you mean by dilating it?
Stretch out.
So normally we're taking it we normally so these variances here are variances over your range in theta. So you can change your variance by changing the region you're looking at. So that definitely improves things. So if you just look at the variance in this region, you're going to have a better scaling in your variance. But if you look at the variance in this region, you're not going to have a better variance. And the question is, you can look at a reduced angle range, but you need to, in order for it to work, you're going to need to look at the reduced angle range close to your minimum. And the question is, well, how do you know where your minimum is in the first place?
Well, my question is, if you do a dilation, that the short noise part also rescaled, same way?
I don't really understand how so you're saying,
Denominator.
but you're still going to be computing your loss at a particular point.
Yeah.
So I don't think that changes the shot noise. Yep.
Okay. So I guess you are also assuming that now the way how you're measuring the variance is that you are sampling from your objective function.
Correct. That's what I'm seeing here.
If you are not in this, you could imagine that you have a super deep circuit doing amplitude estimation. Would you run into a
I want to look in.
problem?
I've literally got one of these papers printed out, and I was going to read it on the plane. I'm curious about other. So I think that's an interesting question to look at. Is estimation strategies that could improve your accuracy, reduce your estimator. And the ones I've seen a few papers that I don't think do it. I think they basically do it the other way around. There is a paper where they reduce the variance due to shot noise, but in turn also reduce the variance of the landscape. So they've sort of made the fallacy in the other direction.
Yeah.
But in general, I think this is an interesting question to see whether there are good ways of doing it. Okay, and third, again on the theme of the variance of the loss isn't the only thing that matters. Important thing to remember is that gradients for gradient's sake is not enough. And you sometimes see this where people are, so just having a lower bound on the gradients isn't enough to ensure trainability, because the point is that the terms leading to the gradients must help to navigate towards the global minima to be useful. So you can imagine this, if you just take your landscape with a bound plateau, so that's kind of shown here, and then if you add in a term that just has loads of local minima and loads of oscillations, so now you're actually going to have gradients, you're going to have non-negligible variance in your gradients, but it's going to be utterly useless because none of those gradients actually help you navigate towards the global minima. They're just introducing local minima. So yeah, we need to be careful when we prove lower bounds that the term that leads to gradients is actually being useful. Okay, so with that in mind, I am going to talk about these two papers. So the first one is on sort of exponential concentration in quantum generative models. The second one on exponential concentration in quantum kernels. And these papers were, I guess, the way we presented them originally is they're sort of user guides for people working in quantum generative modeling and quantum kernels on how to avoid the problems associated with exponential concentration, sort of pitfalls to avoid. Sort of intended really towards the type of people who are really playing around with applications of QML right now. But I appreciate that that is less this audience. This audience is more interested in sort of learning theory. So I'm going to focus more on the second aspect, which is some of the subtleties in how exponential concentration manifests in these settings and sort of lessons we learned from these studies. Okay, so I'm going to start with quantum generative modeling. And I'm sure I hardly need to introduce it to you. One, you're all already using ChatGPT to do your admin tasks for you. And two, Ryan introduced it really nicely earlier. But the core idea here is that you're going to use samples from a target distribution, P of x, to try and learn a model of P of x which can be used to generate new samples. I stole this from my student Manuel, who's into very bad jokes, if you've ever met him. So I'm not responsible for this. And we are going to be interested in the quantum, that should say Born, not Boltzmann, quantum circuit Born machine. So exactly the same model that Ryan introduced earlier, where the idea is that quantum systems, in being inherently probabilistic, are well suited to generative modeling tasks. They're good at producing samples. And we're just going to take a parameterized quantum circuit measured in the computational basis as a parameterized probability distribution, that can be trained and is easy to sample from. Okay, so the idea here is that you've got some target probability distribution, so some probability distribution over stock prices. I also use that example. Then you're going to get your training data from your probability distribution. So these are just going to be sampled bit strings. And then from your sampled bit strings, from your training data, you're going to create the empirical distribution. So that is, you're going to basically create a histogram tallying up the different bit strings, and that's going to give you some probability distribution based on your training data. And then you're going to do the same with your quantum circuit Born machine. So you're going to take your parameterized quantum circuit, you're going to measure it a bunch of times in the computational basis, and then you're going to histogram it up to get your empirical distribution of your model. Then you're going to pick your favorite loss to try and compare and optimize your quantum circuit Born machine. And then the aim is that you might start with a probability distribution that is miles away from your target one, but through training, you're going to get closer and closer. Okay, now the key thing I want to stress is that quantum generative models are what are known as implicit models, but they are currently used with both implicit and explicit losses. Okay, so what do I mean by an explicit or an implicit model and loss? So an explicit model is one where you have access to the probabilities efficiently, so in polynomial time. Whereas implicit models are easy to sample from, but they only give you explicit access to samples. They don't give you explicit access to the probabilities. Now, I'm not an expert in classical machine learning, so don't ask me to defend the characterization of the classical models here. But the key thing I want to stress to you is that quantum circuit Born machines are implicit models. And that is because we do not have access to these probabilities directly. We don't have access to the amplitudes directly, even though on pen and paper we can calculate them. When we actually run this on a quantum computer, all we have access to are samples when we do the measurement at the end. Okay, so this explicit-implicit distinction in terms of models was already in the literature. And what we found in order to understand the trainability of these models was that it was helpful to introduce the distinction between an explicit loss and implicit loss at the level of the losses. So we define an explicit loss, sort of in parallel to the idea of an explicit model. It's going to be one that is defined via probabilities. So it's going to be some function of the probabilities of your target and your model. On the other hand, an implicit loss is going to be defined via samples. So that it is going to be some average over some function of the samples. So examples of an explicit loss include the KL, or the total variational distance, and examples of an implicit loss include the maximal mean discrepancy. And don't worry, I'm going to define these in a few slides' time. Yeah?
But you never have explicit probabilities for your data, right?
Correct.
You don't have your targets, so somehow...
So that's right. So if you are... I guess what you're saying is that... So an explicit loss would work naturally with an explicit model if you had an explicit model. But in practice, you generally, if you're doing quantum generative modeling, you've got only an implicit model. So you're going to have a mismatch if you try and use an explicit loss.
Regardless of... Okay.
You might have estimates of them, though, is what you're going to say. So you do have the empirical estimates based on your histogram.
Sure, but then also implicit can have empirical estimates of the probabilities, right?
The whole point is that this is... Wait, sorry, say that again?
I mean, I can estimate from samples,
yes,
right? The same way that I'm estimating the frequencies in the data, pretending for these things to be probabilities, right?
Yes, so I mean, you can, for example, you could compute this via samples, because you could take your samples, compute your problem, but the point is, it's not a... You basically have to take an average in order to get your probabilities and then do the function. So the point, and those don't commute. So the point is here, this is a function of the probabilities and not the data, whereas this is a function of the samples directly.
Okay, but specifically for MMD, right? If you go into a rich enough kernel,
correct,
you get exactly
the... So what you get in the end is you get something that can be written as a function of the samples and the probabilities. If you think about it, you're going to have the kernels, you're going to have the kernel expression, so you've got both. And the whole point is that explicit, it's only the probabilities and not the samples. You're right, though, that the distinction is a little bit subtle. We spent so long arguing about how to pin it down, and we do it more technically in the manuscript than I've done hand-wavily up here. Yes?
So a question about the access model. So when you say samples, what are you assuming? Are you assuming a unitary preparation circuit that can provide all of those, or are you assuming that there's just some density matrix that flies in from an unknown source?
So we have some initial or zero state, we have a parameterized quantum circuit with respect to some theta value, and then you're going to measure in the computational basis, and that gives you your samples. So that's for your model, or are you worried about the target samples?
And where do the target samples?
Given to you, magic, we don't know. It doesn't matter, we've just got the samples.
So the most powerful model, then, you've got a
We've got
purified oracle that ends up giving you everything you determine.
Or classically, we've got pictures of cats that we do in black and white, we pixelate, and then it's a bit string. Cool, okay. So then our results are formulated using this distinction between explicit losses and implicit losses. I'm not expecting you to take in this table now. I'm going to start talking you through each of the boxes. Okay, so explicit losses, those that are explicitly functions of the probabilities and not the samples. Examples of these include the KL divergence, reverse KL divergence, Jensen's Shannon divergence, total variational distance, and the whole point is these are functions of P and Q. They don't have the X and Y's, the actual bit strings appearing there. Okay, so why can't we apply standard band plateau results directly here? So firstly, the losses are not of the form of a standard VQE style loss. So it's not the expectation of some evolved state and then some observable. And secondly, they're also annoyingly nonlinear, which just makes doing the Haar integrals a bit of a pain. Okay, and also more fundamentally, the exact variance can be non-exponentially vanishing, e.g. this is a plot for the KL divergence, and yet still it not be effective for training. So we sort of see this in practice. So what's going on here? Why can we have a non-vanishing gradient and yet still not be able to train? And here is a hand-wavy argument that I found really helpful in the early stages of the project to try and understand what is going on here. It didn't actually make it into the paper because the others thought it was too hand-wavy. And that is that the log, which is applied at post-processing. So if you're trying to compute this KLD, what you do is you get all your samples, you make your histogram, you get your estimates of your probabilities, and then you play around with the numbers. It's just post-processing to take these probabilities and compute this function. And the log term here, so I've just sort of expanded it out, effectively rescales the landscape to increase its variance. But the problem is, this sort of log that you apply at post-processing also rescales the effect of shot noise. So just sort of chucking in an epsilon to just crudely model the effect of the noise on your estimate, well, when you chuck your estimate in, the log is also going to blow it up. And so it's yes.
So when you're training with respect to KL divergence or the relative entropy, you don't actually ever compute the KL divergence or the relative entropy. You usually deal with the fact that the gradients of it are easier to compute than the function itself. So did you take a look at the gradients as well? That might have been a more relevant argument.
I think the same thing applies there.
Apply,
yeah.
It's just a slightly different argument.
Yes, I think it does, and I think this was just, as I say, we didn't put this in the paper. I'm just trying to give like a 2-second intuition as to why you can see large variances here, and yet that not be enough. Yeah, and so it's exactly the same argument as before, that you might, with this log, increase the variance, but you're also blowing up the effect of shot noise, and so you're left at sort of stage 1. Okay, so we need to analyze trainability differently here, starting directly from the role of shot noise. Okay, and the problem is that with a random ansatz with high probability, the probability of measuring any random bit string x is exponentially small. And you can see this as just the consequences of exponential concentration due to global measurements. So for intuition, just consider a product state ansatz. So we're going to start with the all-zero state, because that's what you do in generative modeling. You're going to apply a product state ansatz, and we're just going to look at the probability of measuring the all-zero bit string. So now let's just make the overlap here for a single term to be equal to r. That's going to be some number that is less than 1, and we're just going to get this power to the n. So we've got that this probability is exponentially concentrating towards 0. And what this means, so assuming that you only have a polynomial number of samples from your target distribution, as is practical, you're not going to have exponentially many, that would be impossible. You are exponentially unlikely for any parameter setting to measure a bit string that's in the data set. So you're just going to have a few target bit strings, and then you keep on sampling from your model, and with exponentially high probability, we proved this, so I think it's intuitively pretty obvious, you're just going to get no overlap. And this means that your loss is independent of theta, and so your gradient is 0 with exponentially high probability. And this, we note, is not just a problem with exponential concentration. Yes?
So could you argue that because your probability has support on a very small subspace, then it's an overkill to use this many qubits, and you could have just used like an effective probability distribution with smaller support?
Okay, so yes, you could do that, and then you've got polynomial samples, you're going to have polynomial support, it's all going to be classically simulable. So you can do that, and then you're just reduced to, then you may as well just do it all classically, and then you could do it all classically and then just run your circuit on the quantum computer to produce samples. So that is an alternative direction you could go in. I don't think it is what most people have in mind, though reading the collective opinion of a community that is not clear on how they expect things to scale is always a bit hard. I think most people have the idea that you're going to have n qubits, a basis of 2 to the n, and then comparatively polynomial samples.
But it's not the only problem, because I mean, if you're happy with the samples you have, then you just sample from the data set, and then there's nothing to learn, right? You need to have a much larger support, otherwise the entire generative problem doesn't make sense. You cannot restrict the space on the data points that you have.
You could still have...
trivialize the problem, that's not what generative.
But you could do poly support and poly samples. You could just be polys and polys. And then you wouldn't have this exponential, with exponentially high probability, you're getting 0 gradients. It would be some polynomial probability, you're getting 0 gradients.
That's not how you use generative modeling, right? You do have an exponential space.
I mean, I agree. But I also agree that what Marco's suggesting you could do, I don't think is that interesting. But we can have this... I don't care. We've insulted each other publicly enough before, it's fine. Okay, oh, I actually had a point to make. Ah, damn it, I deleted that slide. Okay, I'm just going to do the slide without the illustration. Okay, so the point I wanted to say is that this is not just a problem with exponential concentration. So here, these blue things are meant to be your target distribution, and we're showing that, sorry, this is the blue are samples for your model distribution, and we're assuming it's exponentially concentrated, which is why we're basically getting 1 everywhere. You could also have an inductive bias over your model distribution. So imagine actually, they're not all sort of 1s, there's some interesting shape in there. But if that inductive bias is not well aligned with your model, with your target, you're still going to have basically a high probability of no overlap. So even without exponential concentration, if you have a model that doesn't have a good inductive bias, you're still going to get this result, and it's going to be untrainable. This was the figure I was looking for, so that's what I'm showing here. You've got some inductive bias, but it doesn't align with your actual target, and so you still have no overlap. Okay, and so what is normally done is that to avoid infinities when you have no overlap, people introduce this cutoff epsilon, and you just set the ratio to be epsilon in that case. And so what happens is if you have too few shots, you always have no overlap, and so you end up just getting a loss value of log epsilon. And so that's what we see in these numerics here. So initially, if you have too few shots, then you've just got this fixed value of your KL divergence. And what you see is that you need an exponential number of shots, so that's basically marked as going past this dotted line in order to start to get to see a genuine signal. And what's interesting is actually the variance in this sort of really untrainable regime is actually very small, because you're just getting log epsilon every time. You're just getting no, 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 just no overlap. And then you suddenly end up with massive variances in this sort of transition regime, when sometimes you get a very small signal with an overlap, and then a lot of the time you have no overlap. And then eventually, once you're in sort of the proper exponential regime, you get a proper signal, and that's when your KL starts behaving well. And I've done this example for the KL here, but it actually applies for any explicit loss. Okay, so punchline is explicit losses are not trainable with generic models. Okay, so that was the result in that column there.
So
Yes.
just to clarify, this is not specific to quantum models at all, right? This is universally true, everything you've said.
Essentially. The intuition is we formulate it for quantum models.
Just completely, or very much ignored in a large share of the QML generative literature for some reason that also...
It's a really obvious
about.
point that people have been ignoring for some reason. Probably not within this room, but more
Practitioners are
broadly.
very aware of it. They're just so very aware of it because it's hard to train generative models. Everybody knows, right? It's somehow
Wait, so who's aware of it? The classical.
classical guys.
Okay.
Huh?
But also, but also in classical machine learning, I think a lot of model design goes into trying to build implicit models. If you think like a lot of models just like, elbow, all the methods are just trying to circumvent somehow having to deal with explicit models. No? Or would you, yeah.
I mean, I'd say yes, like trying to build inductive bias. And also, people use the MMD more, don't they? They already use... I'll move on. Okay. So implicit losses. So main example of an implicit loss is the maximal mean discrepancy. So roughly, this is a measure of the distance between your target model and your target sample. So you're working explicitly at the level of samples. And what you do is you have this, we focus on a Gaussian kernel, other kernels are available. So this Gaussian kernel compares the distance between two bit strings, one from your target, one from sample, and you compute the average of this kernel over, so the first term is over your model, second one is sort of an overlap term, so it's from your model and your target, and the third one is over both from your target. And sort of whereas with explicit losses, every time you get a sample, basically you're answering a yes/no question, like, is this bit string in the training set? And if there's no overlap, you're just getting no, 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 no every time. In the case of implicit losses, you're asking, is this bit string sigma close to 1 in the training set, where sigma is a bandwidth parameter. And so every sample actually gives you some kind of signal. You actually get information with every bit string you get out. Okay, and then what we want to do is we want to try and understand the trainability of this. And the way we're going to go about it is try and linking it to cost function dependent local and global band plateau results. Yes?
So I want to just raise an example. I mean, like there are some cases where these issues about running into samples from the training set is pretty irrelevant. Like, for example, if you wanted to train to end up building a variational circuit that ends up matching a thermal distribution, right? But you can use the fact that you can compute the log of thermal distribution pretty straightforwardly, and you don't ever run into an issue of not running into the sample for one of the distributions.
So there is a paper recently come out on trainability of quantum Boltzmann machines, which is effectively what you're talking about, and improves trainability guarantees in that case for that model. I am focusing in this explicitly on quantum circuit Born machines, despite the typo earlier on.
Yeah. No, actually, but what I'm referring to is depending on the form of your density operator that you're taking a look at, to do the training to describe your set. Your set may technically contain absolutely every possible configuration, in which case you're never going to have a miss from that perspective. Like the case where you're trying to train an ordinary circuit, not a Boltzmann machine, in order to build thermal distribution. In that case, you've got an explicit form for your training set, i.e. the Gibbs distribution that you'd like to prepare. And so these problems about,
So it's a pure state, though? You're still talking about a pure state?
Yeah, it'd be a mixed state, but the easiest way to deal with it is a purification of the mixed state.
Pure state and mixed, okay, fine.
Right. So I guess all I'm saying is that, I wouldn't view necessarily these problems with the overlap as a fundamental issue with involving approaches with these techniques. Just an issue when you're dealing with one particular set of cases where you only have a finite set of samples from a distribution rather than the entire distribution itself.
Correct. So that's exactly what I'm saying. I'm assuming that we have an implicit model here. What you're now talking about is an explicit model, effectively. And yeah, so the whole way through, I'm assuming that we just have an implicit model. So you just have samples, which is what you have in a lot of the literature on quantum generative modeling. Cool. So we have the MMD. Thing to note is that the MMD can be written as the expectation of an observable. Or at least each of these terms can be written as the expectation of this observable, where I'm basically just writing this kernel in the computational basis. And these states, well, for the first term, these are just going to be the basically your parameterized circuits associated with your model. Second one of them is going to be the parameterized circuit associated with your model. The other is going to basically encode your target distribution. And then for your third term, both are going to be basically the target distributions. Okay, and then once we've got this, we can write the MMD observable, so this thing, in the Pauli basis. So you just write your computational bit strings in terms of sigma z's and identities. And when you expand it out and package up the mess, what you get is an expression of this form. So you have these it's a binomial distribution with these probabilities that depend on your bandwidth parameter, and this D2L term, which includes a lot of mess, but is crucially a 2L body operator. So that is, it acts non-trivially on at most 2L terms. Okay, and now we've got this, we can study whether or not this observable is local or global. And what you can see, you can sort of compute this analytically or you can plot it, is that if sigma is order 1, you end up with this highly global operator, but if sigma scales linearly with the size of your problem, we think the optimal is around n over 4, you get that your MMD observable is a local operator or a low body operator. And then you can plug in sort of global loss function bound plateau results to say that if your bandwidth is order 1, you've got a global loss and it's going to be untrainable, whereas if your bandwidth is order n, you have a local loss and it's going to be trainable. So for product ansatses, we can actually compute the exact expression for the variance of the gradients. And what we see is that the variance, as expected, decreases exponentially for constant bandwidth, but polynomially for linear bandwidth. Sanity check, our numerics and analytics agree perfectly. And then if we actually try and do training, we see that indeed it doesn't work. So if you try and train with a constant bandwidth, just for moderate sized problems, you can't train. But if you train with a sort of order n bandwidth, then training works at all sizes, at least for this simple case. And then we can generalize for deeper ansatser, and we see that at moderate depths, it's trainable, but for deep circuits, then expressivity-induced bound plateaus are going to kick in. Yes?
Are you going to see this issue where it's local, but is the cost still like faithful? Like
Literally 2 slides forward. Yes?
So what you have training steps in the upper right-hand plot. Like where do the training samples come from? What is the problem?
Okay, this is, I think, oh God, which one is this? I think it's learning the cardinality data set, which is all bit and uniform distribution over all bit strings containing n over 2 ones. So it's just a generic problem that we picked. We actually teamed up with CERN and do some learning on a high energy physics problem at the end, but I wasn't going to share those results today. Okay, so these are the results. So we have, yes, implicit losses are trainable for products ansatser. So we got that formally proven. For shallow ansatser, so moderate depth ansatser, we say it's a conjecture based on the fact that we can prove that it is a local loss, and then we plug in basically prior results on local and global bound plateau results. There are a couple subtleties with plugging it in, and so I think partially to be cautious and partially out of laziness, we have called this a conjecture. You can actually prove that the overlap term, the one that really matters, does give you a contribution that is leads to non-vanishing gradients. So I think less cautious people might have just said, look, we have a training guarantee. But we don't have that guarantee currently for the sort of purity terms, for the ones where the extra terms on the side, but not the overlap term. Proving it for those terms too requires generalizing some results from 2 designs to 4 designs, and we weren't feeling sort of masochistic enough at the time to actually do those integrals, but actually I think we probably will do, I imagine, in the review stage. Okay, so that's, and then of course for deep circuits and expressivity-induced bound plateaus kicking in, you can't train. So this was the point that, Jesus, I'm doing badly with time, Marco was bringing up. So our trainability guarantees rely on the fact that the loss is local. But crucially, if you're only looking at local or equivalently low body terms, if these are the only terms that are giving us large gradients, the problem is that these terms only actually match low order marginals. So they only tell us about probabilities between pairs of qubits or 3 qubits. They don't tell us about complex, long range, high order correlations. I'm actually curious, is that obvious to people?
I mean, this is the classical MMD trade-off, no? That like you can't hope to compare distributions efficiently. Like you reduce this to a testing problem against a uniform distribution, and you get all the lower bounds from there. And so the MMD says, okay, if I want efficiency, I have to sacrifice the ability to distinguish certain distributions. And I don't think you can get out of this trade-off.
Well, no, but the MMD is strictly faithful if you're looking at the whole thing. But if you're saying that actually the low-order terms are giving us gradients, but the high-order terms, well, they're just giving us exponentially mentioned gradients that we can't do anything with, it's slightly different.
Okay, but I mean, the MMD also has like, okay, I misunderstood what you were saying, because I thought you had like tuned the MMD to the regime where like the MMD can be 0, but the total variation loss can still be big because you're only matching like sort of low moments.
So it's still going to be, even when you tune the sigma to make sigma order n and it roughly local, it's still technically faithful. But the point is that you're just going to have small contributions to the gradients from the high order correlation terms. And so you're just basically not going to be able to train on those bits.
I think that's a subtle thing that's not obvious.
Okay. Okay, yeah, so just to sort of give a pictorial example, so just imagine 2 distributions on 3 qubits. So these 2 distributions have the same 2 qubit marginals and yet disagree on that they're different distributions. And then the point is if you're only actually doing measurements on 2 qubits at a time, you're not going to be able to distinguish between these 2 distributions. So that is the sort of the large gradients for low body terms only direct towards local minima where you get the low order marginals right, but maybe not the high order marginals. So MMD for linear bandwidths might have non-branching gradients, but that's not enough to ensure trainability towards the global minima. It's potentially just giving you this sort of landscape with lots of local minima, and that's when you're going to want to do things like try and tune your sigma. So start off maybe with sigma order n to get some trainability, and then as you get closer to your solution, crank it down to try and sort of lift up the local minima and guide yourself towards the global minima. Okay, so that was the results in that section. You may have noticed this middle column, what is a quantum strategy? So a potential quantum strategy would be to try and use the quantum fidelity as a loss. 2 problems with this. So it's faithful, just looking at the quantum fidelity, but in its current form, it's not going to be trainable because it requires a global measurement, so you're going to have globality-induced band plateaus. And also, it's kind of cheating in its current form, because if you look, I basically encoded the target distribution into a data state, but if you had that, you've already solved the problem. So you can actually resolve at least the first problem. Yes?
But you told me in the beginning that that was the type of oracle that we can assume we have access
No,
to.
no. Originally, we just assume we have the bit strings.
Oh, so this is just a classical learning problem?
You've got a parameterized quantum circuit involved, and so it is not.
Okay.
Yeah.
Okay. All right.
I'm not advocating these things. I'm sort of, these are things that people do. And I'm saying.
I still don't understand why. Okay, cool. Now I'm on the same page.
Okay, so you can make it trainable, replacing your global measurement with a local measurement. We've got this nice bound here that goes back a couple of years that basically shows that this loss with the local projector is going to be faithful to your global one, in that when your local loss, if your local loss is 0, then your global loss is also going to have to be 0. I thought for a second I got it the wrong way around. And then it's a local loss, you've got trainability guarantees. And maybe this isn't obvious to see, but what we're going to do, and this kind of tackles your problem, so we're not assuming we actually have access to this, but what we're going to do is we're going to rewrite this cost by writing these bit strings in terms of Pauli Z operators. And then what you see when you expand this out is you actually get a cost that can be computed using Hadamard tests. Happy with that? Cool. But again, it's actually not that practical because you're going to need a polynomial number of Hadamard tests for each of the terms in your training data. Okay, so yes, we have a quantum strategy that is going to be trainable, but there are questions about how practical and good it actually is. Okay, this is a summary of quantum generative modeling. So explicit losses are a no-go. Implicit losses can be trainable, but possibly not in a sort of faithful way. You're always going to have expressivity-induced band plateaus, but an alternative approach we might explore, which might appease people like Nathan a bit more is sort of some more genuine quantumly approaches, not just taking these classical costs and sort of slapping them on the quantum problem, but trying to generate genuinely quantum losses. And I'd say that your guys' paper on the Rene entropies would fall under the category of a quantum strategy.
So,
Yes?
what about GANs, which is, sorry, I actually mixed it up the other question as well. So GANs are obviously also implicit loss.
Yes, okay, so
It's a bit more complicated because it has a whole neural network in the loss.
yes, okay, so Chris Zufal and Stefan Werner and a student whose name I've forgotten have a paper that recently came out on this. And they ended up doing a similar analysis to us where they basically write the observable that you get from your neural network as a quantum observable, and then you can study the locality of it, and they can find certain functions for which it does remain local and so trainable. So it's a similar story there. And then I read their paper and gave them comments and was keen to stress the faithfulness point. So yes, they have guarantees about making it local, but then you're only matching low order marginals.
And your local and global argument under what Marco taught us just now is still relevant, or do you have to go
I
into
would
that?
say so. I think my take is that Marco has this nice unifying picture, but as a sort of everyday user, you're still okay to think about
Those are
it.
the traps that you taught us about.
So, but this is for like brick-layered, hardware efficient assets.
This is assuming bricklayer hardware efficient right now, yeah.
It'd be interesting to see how this
Yeah,
changes
exactly,
with, like,
exactly,
other circuits
100%.
with other algebras.
Yeah. Okay, so that was the longer part one. I promise part two will be quicker on quantum kernels. I am not really going to bother to introduce quantum kernels. I assume that most people here are familiar with quantum kernels. The idea here is that you embed your data into quantum states, and then your quantum kernel is a similarity measure between your two quantum states, and your kernel is going to be evaluated on a quantum computer. We focus on two choices in quantum kernels, the fidelity quantum kernel and the projected quantum kernel. So fidelity is just straightforwardly overlap. Projected, actually I'm not going to talk about it today, so we can forget about it. Training kernel methods, so famously the loss landscape is convex, and the best trained model is guaranteed to be found if you have access to the exact kernel values. So does this mean exponential concentration is not an issue here? Sorry, got 15 minutes until the coffee break, so as you might expect, no, it's still problematic. And the issue is that kernels suffer from all the usual sources of concentration. So expressivity, globality, entanglement, and noise. And actually in the paper, the main focus of our paper is running through and detailing exactly how these different causes manifest in quantum kernels. I'm not going to talk about any of that now. I'm just going to get you to take my word for it that, of course, these concentrate as a quantum model. But crucially, the exponential concentration here, in contrast to loss functions, is not over the parameter space, so not over theta, but it's over the data space. So it's sort of the probabilities over the inputs x and x prime. And then, of course, the kernel is estimated with shots. And so what you're going to see is that because your kernel values with high probability concentrate, then in order to distinguish two kernel values corresponding to different data inputs, in general, you're going to need exponential number of shots. So the question happens, what if, as is practical, you don't have a number of shots that are scaling exponentially, but you have some finite amount that maybe you can assume scales polynomially? Okay,
Sorry.
yes?
But that's this old question that people always bring up. That's a very stupid kernel design, and classically, that's a very stupid kernel design. So you should never go for kernels where you compare, if you map your data to really distinct dimensions, you should not do that. Right? So is this not a result that kind of comes out from taking, again, a much too general idea of what a kernel could be?
100%.
Okay.
So it's, there's two different types of kernels here. So we're talking about the fidelity and the projected. But basically what we're saying, so you can say, so you can look at our paper and say, all of these things can lead to concentrated kernels, and obviously those are idiotic things to do.
Like classically as one.
And classically. The point is, lots of people are doing them quantumly. Most people are doing them. No one has a good idea, except for take like encoding discrete logarithm into your kernel. There aren't that many good suggestions around on how to actually get a kernel where you end up with a wide margin that you're going to have things that aren't exponentially concentrating.
one of the issues about wide margins is that, if you believe that you could end up doing this in general, you'd be able to violate state discrimination lower bounds.
Yeah.
So, right? So in this discussion about quantum kernel methods, where does the computational complexity or sample complexity end up coming in for the preparation of the kernel, which prevents you from violating these lower bounds? Right, because if you're doing it on a bit string encoding, I can totally see how kernels end up getting employed in an efficient fashion. But if you've got like an amplitude encoding, you have a nonlinear transformation that these lower bounds forbid. So my question is, what are the set of kernels under your definition that you believe would be actually implementable in polynomial time and samples on a quantum computer?
So that is not a question that we're addressing here. So we're saying we do two things. We point out all the idiotic things you can do that means you can end up with concentration. And then the question is, for this audience, I was going to skip over that. I kind of accept that, don't be an idiot like that. So instead, I'm going to talk about the second thing, which is what happens if you are an idiot here. And actually, we've really enjoyed thinking about this for the last couple of months. And so I was going to present the conclusions of that study, because it's a bit intriguing. I don't know whether it's useful, but we found it fun to think about. So this was the original title of our paper, Exponential Concentration and Untrainability in Quantum Kernel Methods. So we argued that when you've got exponential concentration, it's a bit like barren plateaus, you stop being able to train. But actually, we are genuinely, and I've said this disingenuously many times in my life, and I promise you I'm not just saying it because it's a small community and there's a non-negligible chance that the referee is in this audience. Genuinely, I've said this before. We are genuinely very grateful for the helpful comments of an anonymous referee here. So they questioned whether it was really about trainability, and actually we think they're right. So the key point is that the combination of, and in hindsight it's maybe obvious, but we were in barren plateau world before. So if you have exponential concentration shot noise, then you end up in a trained model where the predictions on unseen data are independent of the input data. So you end up with a model that is, for all intents and purposes, pretty useless. But how exactly this manifests depends on your choice in kernel and your measurement strategy. Okay, so we're going to focus here on the fidelity kernel, and there are two ways in which this could be measured on a quantum computer. So you could go for what we call the Loschmidt echo test, apply the inverse, and then measure the all-zero projector, or you can go for a swap test, or you could go for its the Bell state variant. I can't remember what they call it, destructive, indestructive, the other one. But in this case, you're measuring the Z-Pauli operator. Okay, so if you measure the all-zero projector, it's got eigenvalues 0 and 1, and in the presence of exponential concentration, with only a polynomial shots, you're basically always going to measure you're not going to get the zero projector out. You're always going to get 0 with exponentially high probability over any choice in your inputs x and x prime. In contrast, when you're doing the swap test, your eigenvalues are 1 and -1, and you're going to get 1 or -1 on equal, is roughly an equal amount. So your perturbation, your overlap, mu, is just going to be some perturbation away from the uniform distribution. So basically you get random fluctuations. It's equivalent to tossing a random coin. And the shots you get out are going to be indistinguishable from that of tossing a random coin. And we actually formalized this claim using tools from hypothesis testing. Okay, but crucially, in both cases, the kernel value as measured poly shots is with high probability independent of the input data. Okay, and then this means that the model with only a polynomial shots that you get out at the end is also with high probability independent of the input data. So just taking kernel ridge regression as an example, so you can compute the optimal model. So K here is just the gram matrix, which is going to be effectively a diagonal matrix. In the case of, In the case of doing the Loschmidt echo test, so in both cases you're going to get 1 along the diagonal. In the case of the Loschmidt echo test, you're going to get 0 on the off diagonals. In the case of the swap test, you're just going to get random fluctuations around there. For simplicity, let's consider the limit of 0 regularization. And then if you kind of just plug things through and follow it through, what you see is that the training data labels are trivially cooked into the predictions over the training data. For the Loschmidt echo test, the zero kernel values basically translate to prediction of 0 on unseen inputs, whereas for the swap test, you get predictions fluctuating around 0. So in this sense, exponential concentration leads to poor generalization, not trainability here. So you have sort of cooked in the right outputs on the training data. So in some sense, you have trained well, but you generalize terribly. But it's a really kind of a strange type of generalization in that it's not improved by increasing the amount of input data. Rather, you actually improve your generalization by training on more shots. And we show this in some numerics here. So what we are doing is we've got, this is the test loss as a function of the number of training input pairs. So in the exact case, you see like standard generalization curve. You increase the number of amount of training data, and you see that your test loss goes down. Whereas for the Loschmidt-Echo test or the swap test, you basically got this, well, in the case of the Loschmidt-Echo, just sort of completely constant crap testing error. And in the case of the swap test, you get this weirdly increasing error, but the weirdly increasing error is entirely equivalent to basically just training your kernel on tossing a coin. So that's what the random line shows. And we've got, in the paper, we also work through a very similar argument for the case of the projected quantum kernel. Okay, so that was everything I want to say about quantum kernel methods. There are a number of sources that lead to exponential concentration, which can be summarized as picking your kernel stupidly, picking it without an inductive bias. But we say that, and yet we don't actually have many good suggestions of how to do it well.
So given that you've identified shot noise as being one of the primary drivers of all of this,
Yes.
I guess one of my questions is, do you have any analytic bounds on the impact that shot noise will end up having after n training epochs on this?
It
should
okay.
be relatively easy to do using the inequalities of the diamond distance.
After the number of
Basically the diamond distance that you would end up getting between the ideal channel that updates your model after n steps.
So the way our bounds go is we show basically with a polynomial number of shots and assuming exponential concentration, then the final model you get out in the case of the swap test is statistically indistinguishable from the model you'd get out just by tossing random coins. So those are the structure of our theorems. And in the case of Loschmidt-Echo, you say with high probability, you get out this fixed point model that is data
independent. I
independent.
guess what I'm kind of getting at, right, is how does the scaling with epsilon end up going for all of your estimates, right? And how is that actually propagating in a big O kind of sense?
Okay, no, I think that's interesting. So there's an IBM paper that play around with this, but they crucially make a slightly, they assume this wide margin case. So basically assume that you've got this really nice wide margin from having a clever inductive bias, and the only example they can give of how you produce that is the Cook Shor's algorithm, Cook the discrete logarithm problem into a kernel example. But maybe you could try and take their analysis and apply it to more realistic / not so intelligent cases and see what you get working through it.
I was just wondering, what's known, because your numerics are clear that there's this trend. So there are some easy theoretical bounds.
Cool. I will do my conclusion slides, which are that the QML community is exploring many different learning architectures, and actually the causes of exponential concentration, as wonderfully presented by Marco, are largely similar across platforms. But how it manifests can be subtle, and so actually individual case studies of different loss functions and architectures and training strategies are required. Things to bear in mind on doing so are crucially this interplay of concentration and shot noise. So particularly interesting questions you can ask there are there more better ways we can estimate gradients that have smaller noise with respect to the estimator. Crucially, we cannot forget about local minima. We've got to ask ourselves whether when we have trainability guarantees that give us these lower bounds on the variance, whether those terms are actually pointing us towards anything useful. And finally, and maybe this is a bit niche in the context of kernels, but we found it interesting to think about, how is this problem manifesting? So I guess I'm trying to highlight that exponential concentration doesn't always just lead to trainability issues, it can also lead to generalization issues. And we're not the first people to point this out. This was pointed out in some early works on kernels, but I think we've done quite a nice in-depth study of it. Cool, that's everything, thank you.